Are we missing Alex? No Alex today. There it is. No, Abby? Oh, no, Abby's over here. Sorry, I did see you. Everybody else is good. Okay, guys. Let's do this. Okay, so we talked about calculating the z-scores, right? So I feel like I stopped at an awkward spot. I should probably finish page 2 the other day, but that's okay. We'll finish it now. But this is just using what we had before. So the first example said heights of a group of men are normally distributed with a mean of 69 inches, standard deviation of 3. Find the height whose z-score is 0.6. Interpret the results. Okay, so we're using this formula, or z-score formula. And we know the z-score. We're looking for the x value. So 0.6 equals the score we're looking for minus the mean, which is 69, divided by the standard deviation, which is 3. And then you do a little bit of algebra magic and solve for x. So you end up with x equals 70.8. Okay, so a man 70.8 inches tall has a height of 0.6 standard deviations above the mean. Do you guys have your calculators? Okay, great. A study reported that the length of pregnancy from conception to birth is approximately normally distributed with a mean of 272 days and a standard deviation of 9 days. All right, so if you're looking at your bell curve, the mean is at 272. And when you're doing these types of problems, you need to state it as a probability. So in this one, what proportion of pregnancies is longer than 280 days? God bless you. So you'd say the probability that X is greater than 280. So at 280 here, we are looking for this shaded region over here. What percentage would be above 280 days? It's not looking for discrete. There's not, it's not a binomial situation, so you use normal CDF. The shading starts at 280 and ends at infinity, which would be traumatic if it was a pregnancy. The mean is 272, and the standard deviation is 9. But that is what I'm going to be looking for when you do these types of problems, that you have the bell curve figured completely worked out, that you state the probability and what it looked like in the calculator, and then you just plug it in. Is that what you guys got? 0.187. All right, try the next ones, next one or two on your own. See how you do on those. Okay, look at this with me. Your probability should be written, the probability that 252 is less than x is less than 298. That is normal CDF, going from 252 to 298 with a mean of 272, standard deviation of 9. And here's your sketch of that, and you should get 0.9849. Questions on that? How'd that go? Is it good? All good? All good? Okay. Mensa is an organization whose membership is limited to people whose IQ is in the top 2% of the population. Assume that scores on the IQ test are normally distributed with a mean of 100. A standard deviation of 15. What is the minimum score needed to qualify for membership? When they're asking for score, whether it be just a point or a z-score, we're talking about the numbers on the bottom. We are not talking about the shaded region, which is your area, proportion, probability, p-value. That's all that shaded area up here. This number up here is always going to be between 0 and 1. The numbers down here could anybody's guess, okay? So we are not talking about a z-score. We can see that based on the information, but they are saying the mean's at 100. You're not converting it. You're talking about the highest 2%, so that's going to be over here. This is your area of 2%. They want to know what is the x value there. When you have the x value and you're looking for, when you have the area and you're looking for the x value, that's inverse norm. And again, it depends on what kind of calculator you have, which one you're going to use, which way you'd set this up. If you have an older calculator, you'd have to use the fact that you're going from the far left, so that's going to be 98%. So 0.98, standard deviation of 100, and mean of 100, standard deviation of 15. If you have a newer calculator, you're going to say inverse norm at 2%, so 0.2, 100, 15, and right. So whichever one works for your situation, and you would round this IQ, they round. So 131. And you would want to round up to make sure it's within that last 2%. All right, questions on that? So I feel like we could have done the minutes last time, right? Yep. Okay, so moving right along. If I asked you guys what, how many calories, are you struggling? Let me see. Did I write the right answer? .02. Okay. So if I asked everybody how many calories they ate yesterday, and we took the mean of that, it would be whatever, right? But if somebody was fasting yesterday, that would throw our mean to the lower number, right? It's going to pull that mean over. If somebody was eating a ton of food yesterday, it might be an outlier on the opposite side. If I took whatever number, with or without outliers, and we did that for every class in the high school, and then we took an average of those averages, the outliers would get absorbed. Even though we have people who have gorged themselves or were fasting, that would get absorbed within it. But what's interesting is the average of our room, individually our room, and the average of all of the averages are going to have the same mean. But what's going to change, and I say the same, it's close to the same. What's going to change is your standard deviation, because with an outlier, it's going to pull your data. It's going to pull your mean a little bit too, but it's going to pull your data down, so it's going out wider, and the mean is coming down if you're thinking of it as a bell curve. opposed to the average of all of our averages are going to hold that nice shape. So the standard deviation is what's changing. But taking the average of a bunch of averages is called the sampling distribution. Okay, so this is talking about this tetrahedral die that has 4 sides on it, and they ask you to find the mean of this sample space. Okay, these are your outcomes from one roll, 1, 2, 3, or 4. If you're calculating the mean, you would add those up and divide by 4, right? Which gives you 2.5. To calculate the variance of those outcomes, possible outcomes, remember our notation for variance, is the sum of each of the x values minus the mean, the quantity squared, divided by the sample size. Okay, so if you're talking about this one, and I'm not leaving myself enough room, but so you get the gist. The first number in the sample is 1, so 1 minus the mean, which is 2.5, the quantity squared, plus 2 minus 2.5, the quantity squared. Maybe I did leave myself enough room. 3 minus 2.5. Oh, no, I didn't. Plus, okay, dot, 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 all over 4. If you work that out, you will get 1.25. Okay, so if you were to roll the dice 3 times, you could get 1, 1, 1, you could get 1, 1, 2, 1, 1, 3, 1, 1, 4. These are all of your possible outcomes of rolling the dice 3 times. The average of all of these outcomes, possible outcomes, is 2.5. We won't actually do that, but we would add up all of these averages and take its average, so the sampling distribution, we would get 2.5. We know that because we could have actually done it, or we know that the mean of the sampling distribution, see that notation with the little X bar next to it? That indicates that you're taking the average of averages of the sampling distribution. We know that that is the same as the average of the population. The variance is, well, if we actually put this in the calculator, at one point I had you guys do that. We don't do that anymore. It took way too long. You end up with the variance of being 0.4167. Okay, notice that is not the same as the variance of the population, which was 1.25. What do you notice about the variance of 1.25 of the original population and the variance of the sampling distribution of 0.4167? How can you connect those two values? Somebody will figure it out. What do you got? Similar. 3 times the 1.25? Is that what you're saying? Is that? Because I feel like that would be more than that. But I love that you're trying. But I like, go with 3. There is a 3 involved. What do you think? What do you think? Go the other direction, though. If you knew the... There it is. 1.25. Was that the... Yeah, 1.25 divided by 3 which is equal to your variance divided by 3, and 3 is what? The sample size. Okay. Notice, say it again? Because there were 3, we had 3 dice. So notice this notation for variance of a sampling distribution. It's very exciting, right? You knew what variance notation was, that sigma squared. If you put a little subscript x bar, that means it's the variance of the sampling distribution, calculated as the variance of the population divided by the divided by the sample size. Okay. And as you can imagine, if we would square root that, you would end up with the standard deviation, right? So if we square rooted the top of that, you would get just sigma, which is your standard deviation divided by the square root of your sample size. The standard deviation of the sampling distribution is called standard error. That word is used a lot, so lock that in. And is denoted by this sampling. Notice it just take the squared off the variance. The formula for that is standard deviation divided by the square root of your sample size. Okay, so in summary, the mean of the sampling distribution, which is mu sub x bar, is equal to the mean of the population. The standard deviation of the sampling distribution, so sigma sub x bar, is equal to the standard deviation divided by the square root of the sample size. And the standard deviation is also called standard error of the mean. Good stuff, right? I mean, you can call it the standard deviation of the sampling distribution if you want, but standard error is easier to say. Okay, among the students at a certain college, oh my gosh, let's see. The mean number of hours of television watched per week is 10.5. The standard deviation is 3.6. A simple random sample of 16 is chosen from a study of viewing habits. Let X be the mean number of hours of TV watched by sampled students. Find the mean of the sampling distribution and the standard deviation of the sampling distribution. Find the standard error, in other words. Okay, so the mean of the sampling distributions equal to the mean of the population, which is 10.5. The sample size was 16. Therefore, the standard deviation of the sampling distribution is 3.6 divided by the square root of 16. 0.9. And if you look at the graph of the histogram here of it, there was only one way you could get a 1, right? And a mean of 1 was 3 rolls, 1, 1, 1. There was only one way to get a 4, was 4, 4, 4. But you could have gotten like that 1 point, what was the first one? 1.33. Like if you're looking up here, you could have had this as 1, 2, 2. You could have, I really cannot see that. 1, 2, 1. It's on there. And 2, 1, 1. Oh, there's 2, 1, 1. Oh my gosh, guys. My apologies, I'm blind. But, so you can see how that grows, how it's making that histogram. And then, of course, the next biggest one, how do you get a 2, 2, 1, 2, all that, okay? Anywho, flip it. Sampling distribution of skewed population. Now, if you take a small sample, you can see, if we're only looking at a sampling distribution of 3 classrooms, right, you're going to see that if there's an outlier, it's still going to pull it. As your sample size gets bigger, though, oh, this was the original population. This was just our room. Yeah, there was an outlier because somebody was eating a bunch of McDonald's. Then we took it of just, my room, Duvas and Chestnuts. And you can see we are adding bars to it because it's getting a little more detailed. But that skewed piece is kind of getting absorbed. Then we do 10 classrooms, and you can see, and notice it's honing in here on this x-axis. And then ultimately at 30, that's kind of your key number. If you get a sample size of 30 or more, or you're told that the sample is normal, you can go ahead and use that data with the population mean being the same as your sampling distribution, and the standard deviation, you can use the standard error as, dividing by. Well, and I don't know why I felt like I needed to write this yet one more time, but the mean we could use is the mean of the sampling distribution, and the standard deviation being the standard deviation divided by the square root of the sample size. But you have to know that you have a big enough sample or be told that your distribution is normal to be able to use the central limits theorem. Okay, so it says the first thing you want to do is check your size. If it's appropriate, use the normal curve. If no, then the data is not normal. Use the mean of the sampling distribution and the standard deviation of the sampling distribution. Sketch and shade and find the area under the curve. Okay. So, based on the data of the U.S. Census, the mean age of college student in 2008 was 25 years with a standard deviation of 6.8. The simple random sample of 64 students drawn. What is the probability that the mean age of the students was greater than 26 years? Okay, so this is similar to like that pregnancy one we did. But this was just saying, what is the probability that a woman chosen at random will have a pregnancy that lasts more than 280 days? That would be similar to saying, what is the probability of picking somebody in this classroom that ate more than 3,000 calories? Okay, that would be this. If I said to you, what is the probability that an entire class ate more than 3,000 calories, that the probability of that happening is way more, it's way smaller, right? That's using the sampling distribution. That's where you have to be really careful that you're noticing what's actually being asked. The probability that the sample mean age was greater than 26, that is not where it is. Oh, simple random sample of 64 students. What is the probability that the mean age? It's not saying what's the probability that the age of the student was greater than 26, like one individual student. It's saying that the average age was greater than just 26. Does that make sense? So you have to differentiate between the two. The process is almost the same, except for when you're using normal CDF, you're going to use standard error instead of standard deviation. And that is the biggest mistake students make. They don't know when to use which one.
You use one way you have more of a sample size than the other way.
If you use standard deviation, what it's saying, what is the probability that a person chosen at random does whatever? Or what is the probability that, I don't know, that a loaf of bread has mold on it? Something like that. An individual.
Yeah.
If I said to you, what is the probability that the whole pallet of bread was moldy? That would be the whole group of 100. And they're always going to give you a sample size with those, too. You have to have a sample size to be able to even calculate standard error. So that's kind of a trigger that, oh, I have to use standard error, not just standard deviation. Okay, so your checks. The sample size is 64, which is greater than 30. Therefore, we can use the normal curve. You have to compute the mean. Well, the mean of the sampling distribution is going to be the same as it was for the population. So, what was that, 25? and the standard error. Standard error is the standard deviation of 6.8 divided by the square root of the sample size, which is 64. Okay, so graphically, your mean is 25. You're looking to see the probability that the mean, what are we actually looking for? Probability the sample mean age is greater than 26. So when you write this, probability that the mean, make sure you put it as an X bar, is greater than 26. 26. There we go. So at 26, shade, going to infinity, there we go. That's supposed to be a 6. Okay, so we are using normal CDF, shading from 26 to infinity, where you have an average of 25 and a standard error, throw that down there, of 0.85. The mean. The mean is 25. Because that's what the problem was asking for. And you get 0.119 something, and I can't see what I wrote. Is that a 7? Okay. Thanks. I can't tell if I wrote a 7 or not. Okay, try the next one on your own. Let me see how that goes. Is that what you guys got? 0.001542. So is it unusual or no? It is unusual. Okay. So that was that. And a bag of chips. That's it for the notes for today. True. For the unit. Thanks for your clarification. Any questions on that? How'd it go? Feel so much smarter for it.